If your gradients are wrong, training has no chance. We will sanity check gradients in Python using finite differences step by step. You might see wildly unstable training or loss that does not fall. That usually means a bug in Backprop, not the optimizer. By the end of this video, you will know how to test an analytic gradient against a numerical baseline and catch subtle errors quickly. This saves hours of guessing and speeds up model development. I'm Professor Pi, teaching AI foundations from basics to advanced, with simple, concepts-first Python that helps you solve bigger, real-world problems. Gradients are central to training. If they are wrong, your model learns the wrong thing. Gradient checking using finite differences is a debugging tool. It does not replace tests or good design, but it gives a clear signal about whether your math and code match. We use a tiny loss and compare the gradient computed by your code to a numerical approximation. If they match closely, you can move on with confidence. The intuitive idea is simple. The numerical gradient perturbs each parameter a little bit and measures how the loss changes. That slope estimate is what the analytic gradient should predict. Finite differences can be noisy, so we pick a small step size and watch how the difference behaves. The goal is not perfect equality, but a tiny, principled mismatch that we can explain. We will build a compact gradient checker in 5 small steps. Each step adds a clear capability. Think of it as a checklist you can run on any small model or layer before scaling up. First, set up the problem. This snippet defines a tiny loss and its analytic gradient. This snippet shows a minimal function that returns a scalar loss and also returns the analytic gradient for the parameters. The core idea is to isolate the math you want to verify. The top of the snippet creates a simple parameter vector and computes a loss that is easy to differentiate in your head. Then, a companion function computes the analytic gradient using your usual backprop code or hand-derived derivative. This snippet serves as the ground truth pair, a loss evaluator, and the gradient your implementation claims are correct. Keep this part tiny, so failures are easier to trace. Now compute a numerical gradient. This example computes a naive numerical gradient with forward differences. This example walks through a straightforward finite difference loop. For each parameter index, it adds a small step called h to the parameter, evaluates the loss, and computes the slope as the loss change divided by h. The loop builds a numerical gradient vector by repeating that process for every parameter. The important parameter here is the step size h. If h is too large, the estimate is biased. If h is too small, floating point noise dominates. We will tune h later, but this naive forward differences approach gives a clear baseline to compare against the analytic gradient. Next, compare element-wise differences and find the biggest problem. This code finds the largest mismatch between the two gradients. This code computes the absolute difference between the analytic and numerical gradient entries and then identifies the index with the largest gap. The idea is to focus attention where the mismatch is worst. The snippet also prints the analytic value, the numerical value, and their difference for that index so you can inspect the local computation. When you see a single parameter with a huge error, you can trace which operation or term affects that parameter. This targeted inspection is usually faster than scanning entire tensors by eye. Now adjust the step size to reduce numerical error. This snippet tunes the step size to shrink finite difference error. This part runs the numerical gradient with several h values and tracks how the mismatch changes. The key observation is how the difference behaves as h moves smaller. If the mismatch decreases and then rises, you are seeing the trade-off between bias and floating point noise. The snippet usually reports the best h and the corresponding error. Adjusting h is important because an unlucky choice can hide a correct analytic gradient or falsely flag a correct one. This sweep gives you empirical confidence in the comparison. Finally, automate pass or fail so tests can run in CI. This code turns the comparison into a pass or fail check. The snippet computes a relative or absolute tolerance and asserts that the maximum discrepancy is below that threshold. It prints a clear message on failure with the worst offending index and values so you can debug. The check is conservative. It allows a small mismatch but fails on large discrepancies. This makes the gradient checker usable as an automated unit test you can run on layers or loss functions. It is a cheap safety net to prevent regressions when you refactor or optimize code. After those 5 steps, you can map this pattern to a real project. For a small custom layer or a new loss term, you run the tiny loss and analytic gradient. Compute the numerical baseline. Inspect the worst index. Tune the step size. And then add the automated test to your test suite. In larger systems, run the check on small random inputs and on representative shapes to catch broadcasting or indexing bugs before they affect training. Recap. Gradient checking uses finite differences to verify analytic gradients. Use it when training behaves badly or after implementing new layers. One caveat: finite differences are approximate and depend on step size and floating point limits. Next step. Scale this exact approach by running the check on batches of random inputs and adding timing to measure the cost so you can integrate it into continuous integration. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.